How'd the quiz go?
Great.
Well, I guess it's good news either way, right? Because if you did sucky on this quiz, there's another one coming up in 2 days, right? So you get a chance to redeem yourself. If you did great on this quiz, well, there's another one coming up in 2 days, so you get to do great again. If you have, I'll take questions from homework in a second. Let me kind of update you on what I've done on the website because I made a couple of changes. First of all, there was a slight modification to the homework. I emailed you about this, so if you got that, good. If not, I'll show you now. The only thing I did was I changed the right triangle trigonometry homework to do a couple of the 6.2 problems, okay, which have nothing to do with the unit circle, those particular problems. Otherwise, it's all the same. Okay? For our quiz for our quiz this Wednesday, quiz 2, we'll just do right triangle trig, so all the homework from these 2 boxes here. Okay? And then whatever I covered in lecture last Wednesday, last week. Okay? So our homework so our quiz will be the right triangle trig homework. That's the first thing I changed. The second thing, you'll notice if you look on the website, there are a bunch of study aids down at the bottom. I updated the 127 study aids. If you click on that, you will see sort of review sheets. I will post a review sheet for you probably at the end of this week for our first test. If not at the end of this week, beginning of next week. So the review sheets will be up top. On the left, I have all the topics we're covering updated for this class. Okay. If you scroll down, I have all the topics we're covering, and I went ahead and put the homework right next to the topic as well. So it's right there for you. It's the same as the homework that's on the sheet. You'll see I have the notes that I cover in class, and then I also have the lecture that I videotape every day that we come in. Okay, so you can watch that if it helps. If it doesn't, that's okay. I also have extra practice problems in the 3rd column. These are good just if you want to prepare for the quiz and you want some extra problems. These are good practice. Okay. And then I also have some videos of those extra practice problems, at least for a bit, until I got burnt out last semester. And then I stopped doing such things as you'll see, none. So, but I got some stuff for now. So go to that page and use it to your advantage. If you want. Okay. Today we'll be covering what I call trig functions of obtuse angles, right? So or trig functions of any angle. Okay. In your book, it's covered in both 6.3 and 6.2, right? But the notes are coming from this section right here, trig functions of any angle, and I open them right here. So this is what we will do once we answer questions. So what happened on the homework for right triangle trigonometry? How did it go? What do you need me to do for you? Yeah?
Can you do number 23 for 8.1?
If you tell me what it is.
Sure.
23, 8.1?
Uh-huh.
Okay.
1 minus cosine squared 20 minus cosine squared 7.
And it probably just says simplify or something, evaluate without using a calculator or something like that.
Yep.
This is tricky. Okay. I will do it for you. I'll show you how to do it, and you will go, oh, that's tricky. Before that, if you could, can you read for me number 21? Isn't there one before this?
Yes.
Yeah. Can you give me that one real quick?
Cosine 10 degrees over sine 80 degrees.
Okay. So let's look at this one for a second first, and then maybe we'll be brave enough to conquer this one. So what they're asking you to do here is figure out what number this is equal to. At the end of the day, this is going to be equal to some single number. If it says evaluate, you're supposed to get a single number. Okay? But right now, I have no idea what cosine of 10 degrees is. Okay, the only thing we talked about for cosine and sine for our trig functions were the three special angles, which are 30, 45, and 60. Pi over 4, pi over 3, and pi over 6. This is not 30, 45, or 60, so I cannot actually evaluate this using my definitions. But what I can do is try to make these the same function so that it simplifies. And this is getting at the very last thing we talked about on Wednesday, which is the cofunction identity. So let me quickly pull up these notes. Down at the bottom of these notes, I have this cofunction identities formula. And what the cofunction identities say is if you take a function and its cofunction, they're going to be equal as long as the angles are complements. So, for example, sine of, I don't know, let me make up another number, we'll do that in a second. Sine of 8 degrees is equal to cosine of what? 82. 82 degrees, because these guys add up to 90. They're complementary angles. Similarly, I don't know, secant of 17 degrees is equal to what? Using cofunctions. Cosecant of whatever you need to add up to 90. Right? So take 90 and subtract 17. You get 73 degrees. These are equivalent. Whatever they equal, whatever number this is, and whatever number this is, they're the same number. That's what this is. Because these two angles add to 90. And these guys are cofunctions. So I'm going to apply that same idea here. Sine and cosine are cofunctions, so I can use this same logic to say that sine of 80 degrees is equal to what?
Cosine of 90 degrees minus 80 degrees.
So sine of 80 degrees is equal to its cofunction, cosine of whatever you need to add up to 90, which is going to be what? 10 degrees. So then up in my fraction here, in order to simplify this, I'm going to go ahead and rewrite this as, well, the cosine, let me leave the cosine of 10 degrees the same, but then the sine of 80 degrees, I'm going to replace it with cosine of 10 degrees. And sine of 80, there's no reason to write sine of 80 because I know that it's cosine of 10. So I'm going to replace this with cos 10 degrees. So on the bottom, I get another cos 10 degrees. So this reduces now to 1 because anything over itself is 1. So the point of these exercises, number 21 through whatever this whole section of exercises, is getting you to try and use these cofunction identities to end up with a number at the end of the day, to simplify this to a single number. So I'll do this one next, but questions about this? Okay. This guy is more difficult. This guy really requires the fact that cosine squared plus sine squared is equal to 1. So let me first go ahead and simplify one of these, or change one of these using the cofunction identity. So let's change cosine of 20 degrees. What is cosine of 20 degrees equal to? Sine of 70 degrees. Now what do you think this squared means? What do squareds mean?
The whole function is squared?
Yeah, so cosine squared is the same thing as writing cosine, the whole expression, squared. That's what this means. So multiply that expression times itself. But you really want to think of this as a variable because we have no idea what cosine of 20 degrees is. So this is kind of like a variable square. And this same thing here, this is kind of like the variable cosine of 70 degrees squared. Now as I move on, I'm going to replace one of these. And I'm going to show you some magic. Since I wrote it this way, let me rewrite cosine of 20 degrees as sine of 70 degrees. So in this place here, instead of writing cos 20, I'm crossing it out and I'm writing what it's equal to. So then over here, I'm going to have sine of 70 degrees squared and cosine of 70 degrees squared. Now, all hope may look lost. You may feel inside like life is just overwhelming. Everything is too hard. But let me go ahead and make this a little simpler for you. Instead of sine of 70, I'm going to think about this in terms of a right triangle. Here's 70 degrees. Sine is what over what? Sine is what over what? Opposite over hypotenuse. So in this triangle that I labeled here, sine of 70 is equal to what? I don't know what these lengths are, but because it's a 70-degree right triangle, I'm just going to put opposite over hypotenuse. The whole trick is that cosine of 70 can be evaluated off of the same triangle. What's cosine of 70? Adjacent over hypotenuse. And now, this is the sticker. This whole expression here without this 1 is equal to -1. Now, let's talk about why this is, okay, because this is the whole part. This is the whole reason this is tricky. The squareds aren't super tricky. The 70 and the 30 using the cofunction identity isn't tricky. But realizing that this whole thing here is equal to -1 is tricky. And as we go on, this will become common practice, and you'll know this as an identity that we use all the time. But for now, let me explain it in detail. So, talking about this for a second, what if you just had this? Opposite over hypotenuse squared plus adjacent over hypotenuse squared. Do you know how this simplifies? Can you add those together?
Yes.
What would the common denominator be? Hypotenuse squared, right? You need to think about this as opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. And then if you add these together, your common denominator is hypotenuse squared. What's on top?
Opposite squared and adjacent.
Opposite squared plus adjacent squared. What's opposite squared plus adjacent squared equal? Why? Pythagorean theorem. The Pythagorean theorem in this triangle tells you opposite squared plus adjacent squared equals hypotenuse squared. And hypotenuse squared over hypotenuse squared is most certainly 1. So if these were being added together, they would equal 1. Since there's a minus in front of both of them, since this equals 1, because there's a minus in front of both of them, you can put a minus here, and it has to put a minus over here. That's why negative opposite over hypotenuse squared minus adjacent over hypotenuse squared equals negative 1. So if there's a negative here and a negative here, this equals negative. I have a question for you before you bombard me with questions. Did this blow your mind? Yes, probably. It should have. It's a little complicated if you've never seen it before. Okay. I don't expect you to derive this for me ever at all. Okay. But the one thing that I do expect you to remember from this, and we'll talk about this more when we get into 6.2, is forever and always, if you have sine squared of an angle plus cosine squared of an angle, that will equal 1. This is like one of the golden rules of trigonometry. If you have sine squared of any angle plus cosine squared of any angle, that always equals 1. This is called the Pythagorean identity because it comes from the Pythagorean theorem right here. Right? This was sine, this was cosine, we squared them and they equaled 1. So, full disclosure, this problem was meant, to be done after you've done chapter 6.2. Right? We had it. So, that's why it was different. As far as the quiz goes, I probably, not until we've covered 6.2 will I expect you to be able to do this. But the one before this, the one I erased, 21, the one that didn't have any squares, that one's fair game, that one's fine. Okay, so now, questions? Yes, sir.
With the identity,
Yeah.
does the angles have to be exactly the same on either side? Like, with the sine and cosine down there is 70, do that have to be, could it be like 30 and 60 or?
No, so that's a good question. He's asking, well, I think he's asking, when you take sine squared and you add cosine squared and it equals 1, this identity that I wrote up here, is it possible that you could do this with something like sine squared of 30 degrees plus cosine squared of 40 degrees? Does this equal 1? What do you think? No. Why not? The whole reason this worked out was because this sine and this cosine came from the same right triangle. Okay? But if you have a 30 degrees here and a 40 degrees here, you're not going to have the same right triangle. You're going to have a different right triangle, and then everything's all jacked up. So in order for this to be true, if you square sine, you square cosine, and add them to get 1, the angles have to be exactly the same. Okay, that was tricky. What else? Other questions? What problems did you run into?
Can you do number 29?
Maybe, what was it?
It's trying to solve for the sides in that angle. I just have a confusion on how to find
Oh, okay, I
what
think I know what
function.
you're talking about. I know what you're
Yeah.
talking about. So they gave you a right triangle?
Yeah.
This is number 29, you said?
Uh-huh.
In 8.1? And they give you a right triangle. And they probably give you some information about it. What do they tell you?
It says B equals 5.
B equals 5?
Big B equals 20 degrees.
Okay.
And it says find A and C and A. Okay.
Find A,
C.
C,
Big A.
and B. Okay. And then, how do they label this? Is it like A, B, C, or is it?
Yeah.
So then this is probably big B and big A and big C?
It's actually,
Right triangle?
doesn't matter, that's right, because it's opposite for big A and big B.
Oh, they label this big A?
Yeah.
Not in my book.
Oh, no, never mind, just kidding.
Oh, okay.
Yeah.
Good one. Blow my mind for a second. Okay. All right, so we want to solve, they're giving us two values, and we want to solve for the other three. Okay, we can do that. So first of all, let me fill in what we have. We know in this triangle, big B is 20 degrees, so I'll put 20 degrees here. And little b is 5, so I'll put 5 here. I don't know little a, I don't know little c, and I don't know big A. What's the first thing you can solve for here without any trigonometry? Big A. Right? And I might as well do it since you can, right? This guy we don't know, but because we're in a triangle and we have two of the other angles, we can solve for the third angle. So how do we solve for that?
90 minus 4.
Yeah, so this is 90. So altogether we have 180. Right? Take out 90 from this guy. Take out 20 from this guy. And whatever you have left over has to be big A. So 90 minus another 20, this is 70. Okay. So big A equals 70. 70 degrees. All right, now that takes care of one of them. What about little a and little c? Let's solve for little a. Any idea on how we might be able to solve for little a?
You take the tangent of 20 degrees.
Yeah, so now we're going to have to use a trig function. Okay? Because we know this angle, and because we know this side, right? Think of this, focus on this angle here. You can focus on either one, but let's focus on this angle here. This side is the opposite side with reference to this angle. A is the adjacent side with reference to this angle. So you look at your trig function definitions. Actually, here. You can think, so, you want to find one of your trig functions that relates opposite and adjacent, where the equation, where the definition just has opposite and adjacent. This guy's opposite and hypotenuse, this guy's adjacent and hypotenuse, this guy's opposite and adjacent. So this is the one you want to use to help you solve this problem. So you're going to set up a tangent on it. Tangent of theta, tangent of an angle, is forever and always opposite over adjacent. This is given to you by God or whoever you believe gives you such things. In this particular problem, I know theta that I'm looking at is 20, and I know opposite that I'm looking at is 5. Adjacent is what we call A. So if I want to solve for A, this is the equation I'll set up. And then, because I'm trying to solve for A, I would multiply both sides by A to clear my denominator. Remember, tangent of 20, I don't know what it is, but it's some ratio, it's some value, some number. So to isolate A, I can divide by that number. Right? Because this is connected by multiplication, so I can divide this over to the other side. So A is equal to 5 over tangent of 20 degrees. And if you have a calculator, you can input this and get an approximation. When you're using your calculator for something like this, make sure you're in degree mode. Let's see what Google tells me. 5 divided by tan of 20 degrees. I don't know if Google's in degree mode. Here, Google. Google thinks 13.74 or whatever they told you to round to. Do I have a confirmation?
Yeah.
Yeah.
So that would be A. That's how I would solve for A. This is, if you've never seen this before, this is a slightly sophisticated argument. So kind of the idea is, if you have an angle and a side, you can solve for any other side if you use trig functions. So once you have an angle and a side in a right triangle, you can solve for either of the other sides using one of your trig functions.
Would something like this be on the
Yes.
quiz?
Yes, this is fair. Now I haven't finished, right? Because I need big C. Or little c, excuse me, I have big C, it's not. I need little c. There's two technically there's three. But there's two different ways really to get little c at this point. You know what there are? You could use the Pythagorean theorem, right? Because you have an approximation for little a. We learned that little a is approximately 13.74. So you can use the Pythagorean theorem and get little c. Yeah, I probably wouldn't use the Pythagorean theorem. You know why? Yeah, you're going to use this approximation to get your next side length, which means you're going to compound your error. Right? You're using something that has a little bit of error in it to get another answer, so that answer is also going to have error. Compounding from this. What you could do instead is set up another trig argument. I like this way better because it uses trig. Right? So over here, focus on the 20-degree angle again. But now instead of opposite and adjacent, think about opposite and hypotenuse. Right? Because this is what you're trying to find. Right. So now you look at your trig functions. Which one of these uses opposite and hypotenuse? Boom. Sine. So I don't know why I'm doing that. So, in general, sine of theta is opposite over hypotenuse. In our particular triangle, sine of 20 degrees is 5 over c, right? That's what I don't know. And you can use all the same strategies to solve for c. You know, you got to multiply it up, and then you got to bring the sine 20 down. C gets multiplied up. C times sine 20 equals 5, so then the sine 20 gets divided down. So C equals 5 over sine 20, which is approximately, anybody want to do it for me? Say it.
14.62.
14.62 or something like that.
How do you know not to use cosine?
You could use cosine. What would you do for cosine? Now, if you use cosine of 20, then you're running into the same problem that you have with the Pythagorean theorem, meaning that cosine of 20 is going to require this approximated side. You can do it, and I'll even probably give you full credit for doing it. It's just not a good idea. You might as well use this side since this is given and not approximated. So any way you can use this side would be okay. However, you could still use cosine and this side. Well, how could you set up a cosine argument using this side? Cosine of 70 degrees. Right, so if you love cosine, right, that's your guy, your go-to guy. You could set up a cosine argument by focusing on the 70. If you focus on this angle, this guy now becomes adjacent because he's touching the 70-degree angle. This guy is still hypotenuse because he's across from the 90. So you could set up cosine of 70 degrees equals 5 over c. These are the same equations. How do you know these are the same equations? They're co-functions and the angles add up to 90. So, I mean, these are the same quantities on the left. So this will get you the same thing. Yes?
On the tests or quizzes, do you
Yes.
prefer the exact or the estimation?
Well, I kind of prefer the exact, but since they're going to be multiple choice, it'll just be whichever one I give you on the quizzes. It's good to have them both for me. All right, solve for it exactly and then get an estimation. That's just good practice. What's it say?
Tangent 20 degrees
Keep going.
minus cosine 70 degrees over cosine 20 degrees.
All right, let's try that one. I wanted to assess whether it was worth my time. I'm still not sure. This is number 25. So you said tangent of 20 degrees?
Yep.
Minus or plus?
Minus cosine 70 degrees over cosine 20 degrees.
So remember, the goal here, you don't know, you want to do this without a calculator. You want to do this without approximating any of these. So you have to somehow get them to be like terms, get them to be something that you can collect. Right? Right now, so right now, this has a 20 degrees, and this has a 20 degrees, and this has a 70 degrees. So what I'm going to do is change this to change the top of this guy from cosine to something that has 20 degrees in it. So what's the top equal to? Sine 20 degrees. Does that make sense? Because they're co-functions, so you choose an angle that adds to 90. So now I'm going to go to my triangle, because I can't do much else. I can't, everything's 20 degrees, so I can't change any, I don't want to change any of the other angles. I'm going to go to a triangle, and I'm going to say, here's 20 degrees. Here's, according to 20 degrees, this is adjacent, this is opposite, and this is hypotenuse. So in for tangent, what is tangent of 20 equal to in terms of these three words? Okay, so for this triangle, which has a 20-degree acute angle, tangent is equal to opposite over adjacent. But in that same triangle, what's sine of, because 20 is the same angle, so in that same triangle I can talk about sine of 20. Opposite over hypotenuse. I can also talk about cosine of 20. What's cosine of 20? Adjacent over hypotenuse. But these are in a fraction. So I really have a fraction over a fraction. How do you simplify a fraction over a fraction? Multiply by the reciprocal. Or the multiplicative inverse, I guess you could call it. But here, what I'm going to do is I'm going to get rid of this division on the bottom, and I'm going to multiply up top. Okay, so I'm going to get rid of this and change it to multiplication by hypotenuse over adjacent. So what happens? This opposite over adjacent, this guy didn't touch. So let me recopy him. Yeah! Look at what happens here. You have a hypotenuse on top and a hypotenuse on bottom. So all you're left with is an opposite on top and an adjacent on bottom. This guy is supposed to simplify very quickly once we get some identities under our belt. But what did this turn into at the end of the day? Tangent, right? It turned into an opposite over adjacent. Right? So actually, whenever you have sine over cosine, the same kind of simplification works, and this becomes tangent. stop you there. Make sure, I'm going to do one more example from right triangle trigonometry, and then I'll move on and talk about 6.3. But make sure when you do the homework that you go back and do the stuff from 6.2. Okay, 31, 32, 35, 36, 37, 38, 41. You can do all those. Or should be able to do all those. Before I move on to 6.3, right, this trig functions of obtuse angles, I want to give you one more review of them. Because you didn't ask, you didn't ask me anything that reviewed this, so I didn't make one up for you. So I want you to find the exact value of and then I'll give you an expression. Let's do cosine of 60, oh no, let's do radians. Cosine of pi over 3 times sine of pi over 6 minus tangent of pi over 4 times secant of pi over 6. So, the intention of this problem, even though you could maybe try to be slick with cofunction identities and all that, the intention of this problem is not for you to use any identities at all because these are all special angles. The intention is for you to actually evaluate what each of these trig functions is at that angle. If you recall, we talked about how to evaluate sine of 30 degrees, or cosine of 60 degrees, or sine of 45 degrees. All right, how did we do that? What did that depend on? So, if you want to evaluate something like sine of 30 degrees, you need a right triangle with a 30-degree angle in it. So if you remember, we developed two special right triangles. One of our special right triangles is a 45-45 right triangle. What were the side lengths that we used here? Yeah, we assumed this was 1, which means this had to be 1, and then after the Pythagorean theorem, this became root 2. One other important thing to notice about this triangle is that 45 degrees is the same as what in radians?
Pi over 4.
Pi over 4. This guy's also pi. So that was one of the triangles you could use to evaluate sine and cosine. Okay, this was for 45 degrees. The other triangle had a 30-degree angle in it. Across from the 30-degree angle, we put a 1. What were the other side lengths?
2.
Oh.
1.
Ooh. Yeah. So this guy ended up being 2, and then this guy ended up being root 3. And remember, if this is a 30-degree angle, then this guy up here is 60 degrees. What about in radians? What does these become? Pi over 6. Pi over 3. So over here, for example, if I wanted sine of 30 degrees, I would first pick my triangle. This one looks good, because it has a 30-degree angle in it. And then I would use the fact that sine is opposite over hypotenuse. So I would pick off the opposite side and the hypotenuse. This is 1/2. I'm going to get to this. But sine, cosine, tangent, secant, cosecant, cotangent of 30 degrees, 60 degrees, 45 degrees, you need to have memorized. You need to know those for your quiz. Which means the easiest way to memorize those is to know these two triangles, because all the information is in these two triangles. And then the only other thing you really need to know is the definitions. Right, once, if I want you to evaluate sine of 45 degrees, all you do is go to your 45-degree right triangle. Sine is opposite over hypotenuse, 1 over root 2. Rationalize the denominator, but then we'll be done. So if I did not make this clear yesterday, let me make it clear now. These are really good to have memorized. And they will help you evaluate things like this with poise. Let's say it that way. Without panicking. Now, let's actually go through and evaluate this. The first thing you want to understand on a big expression like this, keep track of your operations, okay? This is one quantity and this is one quantity. You're going to figure out what cosine of pi over 3 is. You're going to figure out what sine of pi over 6 is, and then you're going to multiply. Okay? You're going to figure out what tangent of pi over 4 is and what secant of pi over 6 is and multiply. And then you subtract the results. So to do cosine of pi over 3, cosine is always going to be adjacent over hypotenuse, and I just have to pick the right triangle. Pi over 4, pi over 4, pi over 6, pi over 3. Cosine is adjacent over hypotenuse, so according to the pi over 3 angle, adjacent is which side length? 1, 2, or root 3?
1.
1 is adjacent because it's the one that's touching the pi over 3 angle. So cosine will be adjacent over hypotenuse. 1 over 2. Times, right? So I figured out what this guy was. Now I have to go in and figure out what this guy is. Right? Sine is always what over what? Opposite over hypotenuse. How did I know that? It's right here. OH, opposite over hypotenuse. But for a pi over 6 angle, I'll go to this, I'll focus on this angle right here. Opposite, again, is 1 because that's the side that's opposite pi over 6. Hypotenuse is 2. Minus, then do each of these. Tangent of pi over 4. Tangent is forever and always opposite over adjacent. So I do opposite over adjacent, but I do it with a triangle that has pi over 4, a right triangle with a pi over 4 angle. Focus on this guy, opposite is 1, adjacent is 1. Times, all right, secant.
Hypotenuse over adjacent. Hypotenuse over adjacent.
Yeah, so secant is the reciprocal of cosine. Right? Remember the way this works, each one of these has a reciprocal function. Right? A function you get by flipping this definition. So this guy has cosecant as his reciprocal, this guy has secant as his reciprocal, and this guy has cotangent as his reciprocal. And to get cosecant, you have to flip this definition. So instead of opposite over hypotenuse, you would do hypotenuse over opposite. And instead of adjacent over hypotenuse, you would do hypotenuse over adjacent, and then adjacent over opposite. So as long as you remember how these match up, and remember the S and the C switches, then you know the definition of your reciprocal. So over here, when I do secant, instead of doing adjacent over hypotenuse, I'm going to do hypotenuse over adjacent. Which is, for my pi over 6 angle, hypotenuse 2, root 3 adjacent. So far so good? So all of these evaluations depend on two things, understanding the definitions and understanding these right triangles. The next thing you're going to want to do is simplify this, because this is kind of ugly. 1/2 times 1/2 is 1/4. Hopefully that's not blowing anybody's mind. Straight across for fractions when you multiply. 1 over 1 times 2 over root 3 is just 2 over root 3. Now I do want to combine these. Okay? And before I combine these, I'm going to get rid of this root 3 in the denominator. I hate roots in the denominator. I always want to rationalize. So how do I get rid of this root 3 in the denominator? Multiply by root 3 over root 3, like this. So this is 1/4, right, just recopy this, minus 2 root 3 over 3. And then we're going to write this as one fraction because we can. It's good practice. How do you write this as one fraction?
Common denominator.
Common D. How do you get common denominator here? What is it? 12. Which means this guy's got to become a 12. So times 3 times 3. This guy's got to become a 12. Times 4 times 4. So altogether I have 3 12ths minus what?
8 square root of
8 root 3 over 12. This 4 is not under a radical. He's a whole number. He gets multiplied with this coefficient here, not inside the radical. So that's why it becomes 8 root 3. And then if you combine these, it's 3 minus 8 root 3. Ooh, chocolate.
So,
Needle pulling
I have a
thread.
question. When you multiply two numbers
Yeah.
under the root, does
Yeah.
that just,
Yeah,
does
so
that just get rid of the root?
yeah, it depends. So so as far as multiplying radicals goes, like if you have root 2 times root 2, if they're exactly the same number underneath and exactly the same radical, then sort of the magic behind the scenes here, this is becoming root 4 because you do 2 times 2. But then the square root of 4 is 2. So kind of the quick, I don't know if I'd call it a trick, but kind of the property here is if you multiply a square root by exactly the same thing, the square root goes away.
Oh, that's why. Okay.
So on the bottom here, when I did root 3 times root 3, really it's root 9, but after I take the square root of 9, I get 3. Yes?
I may have forgotten, but is it wrong if you subtract 3 from 8?
Oh, yes, that's massively incorrect. So, this 3 and this, you have to follow your order of operations. Okay? If you want to subtract these, you would have to multiply these first. Right? Because multiplication, this is multiplication, and multiplication happens before addition or subtraction. But you cannot multiply these because this is unknown, irrational. So kind of the rule is you treat radicals like x's. Right? If you had 3 minus 8x, these are not like terms, right? You can't collect. Same thing with 3 minus 8 root 3. These are not like terms.